for everyone out in the internet land, your schedules should be live, and the list of courses should all be live right now. Just to be aware, you should be able to start to go through those and see with certainty now which courses are going to be online and which ones are not. So just be aware that I think that happened today. Moving forward, I guess. Let's talk about epoxides, I guess, are the next thing that we have to do. Let me fix this paper. When we look at epoxides, we are looking at the reactions that are found right down here in preparations of epoxides. And then we're going to have to go into this section. Oh, yikes, that got a little... I'll fix that. Then we're going to jump into reactions of epoxides, which is all of these reactions. Yikes, now the opposite problem right here. And what I'm going to hopefully do for you during this section is really tie together all of these ideas because they become really thematically the same. Everything over here is attacked by a nucleophile first. Everything over here is attacked by acid first. And so what we learned from this portion right here is going to be massively applicable to what we do over here. And so when we look, I've kind of gone through and started to, for the 7 people that are here, started to lob off reactions that I don't want you to focus your efforts on now. This horse, we beat that. It's dead. Done. Autooxidation, not a horse. Not going to beat it. Not even involved. This enantioselective epoxidation, this is quite possibly... And we're not going to study it because it's not really all that interesting from a general organic chemistry. But this is, let me just explain this real briefly. You won't see this on the examination either. This one is a beautiful, beautiful stallion. If you play Breath of the Wild, it's the giant black stallion in Breath of the Wild. We don't beat that with a stick, okay? And so this one right here was developed by K. Barry Sharpless. And K. Barry Sharpless developed a way that by mixing in his organic solution, tartaric acid, that you could influence the selection and the epoxidation here such that you would generate just the R or just the S selectively. And so when you're trying to make drugs that rely on chiral centers, if you can instill a chiral center some way and get like 95% enantioselectivity, that makes a huge impact on profit margin, right? If you were going to get a 50-50 mixture of R and S, and now you can get a 95-5, you recapture 45% of your lost product, and that's huge. And so that reaction was developed, and I believe he won the Nobel Prize for that. I can't remember. I'm pretty positive he did when I was in graduate school. But for us, the only thing we're going to worry about for preparations of epoxides, just like we only worried about Williamson ether synthesis, we're only going to worry about these 2 different ways of making a epoxide. Okay? And so, new functional group, epoxides. And so just like we had done previously with our ethers, let's just talk about what an epoxide is. It is this 3-membered ring arrangement of an oxygen bound between 2 carbon atoms. And what you will find is that we could have substitution at any of these places where I've denoted as wedges and dashes. Okay, and I'm not going to go into that quite yet, but just be aware that is the epoxide, and you could have carbon residues at really any of these points along the way. We have to talk about reactions of and what we're going to find here is that there's two types. Nucleophile is added first, followed by acidification. And then option 2 is acidification first, followed by nucleophilic attack. And that's something we'll get into in just a little while. The other thing that we must then talk about is the preparation. And there's two different types of preparation of epoxides. One is from, let's do this, from alkenes, and the other, well actually, let me correct this. Both of them start with alkenes, and they're two separate pathways that we could undergo with that alkene. So we're going to start with alkenes, and we could essentially use a halohydrin followed by a base, or we could use peroxy acids to make epoxides. And so that's what's being summarized when we zoom out of the K-Berry sharpless work into this portion of our reactions that you have to know for this unit. We're looking at either this right here, which is our peroxy acid use, or we're using halohydrin formation and sodium hydroxide. And so let's just review how we could possibly take what we learned with alkenes 2 units ago, just 2 weeks ago, and see what treatment a base would do to that. And then I'll just briefly talk about how peroxy acids could be used. But when we start here, let's take a look at the preparation and then go a little bit further into some of the other important aspects, which are the regiochemistry and the stereochemistry of these reactions. So when we look at preparation, we will be starting with an alkene. And so what I want to do is just pick and denote an alkene like this. So we'll be starting with an alkene. And regardless of what method we use, and just see above, it's this stuff right up here, we will end up generating an epoxide like this. And what I'm going to do is I'm just going to put this hydrogen right here because I want to be careful to denote that this hydrogen will stay on a wedge with respect to this. Certainly there's a hydrogen here, so the center is not chiral, so it doesn't really matter at this point in time. But because I don't want to add another, I need to preserve something right here to illustrate proper halohydrin formation here. I just want to keep track of 1 proton on the wedge, but just don't think it's chiral or anything. I want to be able to keep track of that. Now I made it too big. Great job. Epoxide. Regiochemistry. The region of the molecule that this occurs over is the alkene. The alkene portion, if we were to say carbons 1 and 2 here, 1, 2, we are looking at carbons 1 and 2 here. Most importantly, the sigma structure of the alkene does not change. All right, there will be no breaking of any sigma bonds during this process. No sigma bonds will be harmed in the making of this product. And so when we look at hey, look, this carbon to carbon 1 is the same. That never changed. This whole residue here is still the same. The carbon 1 to carbon 2 sigma bond, carbon 2 to carbon to hydrogen, those sigma bonds all stay the same. So those sigma bond scaffold remains the same. And so that's where the regiochemistry is. Stereochemistry, I'm just going to write same side of alkene, same side of wedge or dash. The idea being that if you have cis, you will have, I've never done this, you will have wedge. And if you had a trans alkene here, you would have a wedge dash type arrangement. You'll never see that in a textbook, but certainly as a visual identifier of what could possibly take place, denoting something as a wedge or a wedge dash about carbons 1 and 2. I think that's probably still fair. I don't think you guys are freaking out about any of that. So general overall view of the regiochemistry, stereochemistry, functional group transformation that's involved in these reactions. I just want to take a look mechanistically then at a specific reaction, the halohydrin formation, because it's the exact same chemistry as the Williamson ether synthesis. I just ruined it. That was the take-home message. But regardless, it's the same chemistry as the Williamson ether synthesis. We just end up doing an intramolecular ring closure rather than an intermolecular covalent bond formation, joining two molecules. And let's just take this example right here. Starting with this alkene that we had, with Br2 first, followed by water, and then treatment with base NaOH, and we should be able to generate an epoxide like this, which would feature, for reference point, those things that were on the same side have now been migrated to the wedges, even though this is not chiral. So when we look at the mechanism for that, starting with this six-membered ring, alkene, the behavior that we have come to know when we react that alkene with that bromine is that alkene will behave as a nucleophile, and that because these bromine atoms are not shared equally at all times, we are looking at a very static representation of a very, very dynamic process, then we would expect to see some type of nucleophilic attack and perhaps bond breakage in order to form this weird looking bromine thing that was attached like this in some textbooks that you might have seen. I think our textbook does something like this weirdness that ends up happening, but eventually what I kind of told you is that I really envision this thing as just the bromine adding Markovnikov type addition to form a carbocation on the more stable position. And so once we formed that carbocation, we now have a very good electrophile that we could potentially react with any nucleophile that's in solution, which would be our water. And we would see addition there, because this behaves as our nucleophile, to make our halohydrin. This is so cool. Oxygen here, and this whole thing is protonated at the end of that step. And now we've shown that HBr could come in, or Br minus, the one that we had right here, could come in and remove this proton. But the best way to illustrate this is with the counter anion that is formed, because this is what's going to come out in solution from your reaction. And I might have mentioned before that, in your separatory funnel, when you're shaking your separatory funnel, that's when we're going to likely see the most what was I saying? That's when you'll see the deprotonation happen. You'd maybe mix something like sodium bicarbonate in with your solution. In this case right here, we wouldn't add the sodium bicarbonate because we are going to add NaOH to our solution. And that's the second step here, this NaOH. And the first equivalent of NaOH, we should expect this species right here to behave as a Bronsted-Lowry base. And we have a Bronsted-Lowry acid. And so we should anticipate deprotonation to form our regular alcohol, and our bromine, just like this. And it turns out that if we have copious amounts of OH present, if I were just to illustrate this with the bond there, I'd have something that I could deprotonate. So let me redraw that with the hydrogen here. I could deprotonate this, yoink. Well, I should have drawn that in orange, but that's all right. Here, all of a sudden now, we have a strong nucleophile directly attached and adjacent to a very electrophilic center, or partially electrophilic center, with a leaving group that's attached. And so you just see an intramolecular ring closure, loss of leaving group, and you have formed that epoxide as a result. And so that set of reaction conditions, mechanistically, it's really the same as our Williamson ether synthesis. We have deprotonation, and then addition of the alkoxide to an alkyl halide to make an ether. And here we have deprotonation to make a strong nucleophile, alkyl halide addition to make an epoxide. So very similar to what you've already seen with Williamson ether. It's just kind of the combination of really reactions that you've seen from OChem, or the first part unit, and then just deprotonation after that. What about use of peroxy acids instead? Let's see, this 5-membered ring here with an alkene, and adding this is what a peroxy acid is. It's a carboxylic acid with an additional H present. Lies, O present in between, an additional oxygen atom in between the carbonyl center and the oxygen of the OH. And they have some really cool properties by which I won't go into all that specifically, but they end up making an epoxide as a result. And that's all I want you to know. There's this really cool mechanism that these reactions an intermediate that this species goes through. Did I start drawing that incorrectly? I don't think so. Yeah. This peroxy acid has a way of coordinating in such a manner. I'm drawing dash lines here so I don't have to fully commit to an idea until I've sketched it all out whilst still talking here. But what ends up happening is the species coordinates in this really cool way. Yep, that should have been dashed. To kind of insert an oxygen atom using this pi scaffold. And so we'd kind of see something like this. This weird coordination of this peroxy acid, and then one of these oxygens essentially inserts itself all in this one concerted mechanism, and it's not necessarily the most beautiful mechanism in the world, but just owning that there's two different ways to make the peroxy acid. And again, why do these two different methods exist when you look at this bottom left corner? One reason why these methods exist is you have one reaction pathway that can be conducted in the presence of water for molecules that are soluble in water, and one set of reactions that are conducted in organic solvent for molecules that are insoluble in water. And so that's why those two pathways exist. I don't want you to memorize the mechanism for this. I just want you to know that this peroxy acid is one way of generating an epoxide, and it has the same regiochemical considerations that we would expect to see when we take a look at the hydrobromination, and then followed by base. It's really quite essentially the same reaction. If we're done with the epoxides, then let's take a look at the reactions of epoxides. So reactions of epoxides. When we look at reactions of epoxides, what I am going to do is I'm going to illustrate this with an asymmetrical epoxide. And we're going to suggest that this thing can undergo a set of reactions to make a bunch of different products. And these reactions are captured right here. And you can see we're generating a bunch of different types of species that molecules that are difunctional and consists of typically an OH and something else. And what I mean by that is we're taking an epoxide right here and we're breaking it in the presence of all of these things to make essentially an alcohol in every single one of these cases. And then we also make some new heteroatom or carbon or sulfur or carbon or hydrogen or halogen or oxygen bonds as well. And so there's a number of different species. This would be an ether. This would be a thiol, a cyanide, just a carbon-carbon bond, a halogen. There's a number of different functionalities that'll be produced using these different types of methods. And so let's see. What I want to say is that these reactions, and this is something that I've already written, there are two types of reaction pathways that could occur. And when you're looking at the chart in the bottom left-hand corner, what you're seeing here is that there are two pathways. One pathway pathway number 1 involves the addition of the nucleophile first, followed by the addition of water, and I'll just do this, HOH. Or the other possible pathway that these reactions can undergo first is the addition of the acid in the presence of a weak nucleophile. And so what you're going to see with these reactions is the presence of some type of acid that will be combined with some type of a weak nucleophile. And these are the three reactions that are on the right under this acid catalyzed conditions in that chart. So if we're splitting up all of these reactions into two really different ways, then can we talk about the regiochemistry and stereochemistry that results? So when we start with an epoxide and we end up generating or going through these two different possible pathways, the regiochemistry is such that it appears to me like Let's deduce this. Let's come back and fill this information in as we start to discuss these two different mechanistic approaches. And so we'll come back and hopefully fill this information in. Here's what's likely going to happen. We're going to go through all of these reactions that are shown right here in generalization, and then I'm going to tell you class is over and have completely forgotten to write in the summaries here, and you'll see them when you see the notes online with no discussion of it. Hopefully I won't forget to do that, but I know myself. And so let's take a look at the mechanistic pathway that joins all of the reactions on the left that say strong nucleophile next to them. What happens when epoxides react with strong nucleophiles first? And so pathway number 1. And again, I really like to keep reminding students of this because, well, first of all, if you're here right now listening to me and you want to go to medical school, great. What you need to know about yourself right now, or dental school or vet school or anything you're trying to do, is 2/3 of the class do not attend these sessions live. So when you're competing against other students to get into medical school, you waking up at 9 o'clock to attend these sessions puts you in the upper third of your classmates already, and these differentiations come out. Why does this stuff matter then when you look at medical school and dental school? You have a patient an epoxide that could present itself in two different ways under these conditions here or these conditions here. And if they present this way or if they present this way, there are a number of different ailments that occur, of which should be treated accordingly. And so you have to classify things. You have to categorize things on basics of importance. You have to be able to look at similarities and be able to see nuance. And so what separates me from what you're going to be as a doctor someday? Well, I just don't like humans, and so I stick with epoxides. But you're going to have to worry about the human impact of your work. And so this skill set I'm teaching you, yeah, it's low stakes, because I'm low stakes, on carbon atoms. But if you can develop this skill set now, when you replace this epoxide with a person that's ailing, you're going to have a skill set that you can rely on. And yeah, then this skill set I'm teaching you now, you're going to replace it with human considerations. But at least I'm starting to teach you a method of looking at something new and the vast array of things that can happen, and helping you learn ways to filter and focus to the important part. And the important part for us is that all reactions of epoxides could be these two different types, of which we have a mechanism, and then it's going to be your job to figure out how that mechanism applies to some nuance between these different types. And it certainly is applicable when you go to medical school. I have graduated 3 doctors now, 2 dentists. I have 2 students in vet school, and they all tell me that because they worked hard in OChem, they had a good skill set to succeed in these other schools. It didn't make it easy, but they had a skill set. And if I can give you that skill set to be successful now and in the future, then I've done my job. I don't care if you remember the OChem. Pathway 1. We have an epoxide that we could potentially react. Let me change this up here to a hydrogen. We have an epoxide that could potentially react with a nucleophile. And so I'm going to denote that nucleophile as Nu with a minus. And these nucleophiles for this reaction, let's take a look at the bottom left corner. Your nucleophile could be an RO minus. And then there's just this counter ion, this sodium ion that's next to it. It could be a C triple bond N with a minus with a sodium ion next to it. It could be a sulfur-bearing nucleophile with a sodium next to it. It could be a much weaker nucleophile, like a Grignard. You've seen Grignards before. And it could be this R partial minus MgBr type thing as your nucleophile. Or it could be a hydride, which we would add as lithium aluminum hydride. Can I fix this one? Hey. Lithium aluminum hydride. And so remembering that you have like an R partial minus here and an H minus here. So obviously nucleophiles along each and every single one of those points. Well, how does a nucleophile react with an epoxide? Well, it turns out that this epoxide has 2 electrophilic carbons on it. Is there any surprise to that statement? I don't think so, because you have a carbon-oxygen bond. An oxygen is not a carbon, and so the electrons that are shared between that carbon and the oxygen, they aren't shared equally. And so they're going to favor the more electronegative atom, oxygen. So we have partial positives at each of these positions. Sterically accessible. Sterically hindered. Only one of those positions is more accessible. Nucleophilic attack at that position. We see breakage of the carbon-oxygen bond. There's a lot of ring strain that occurs in a carbon-oxygen 3-membered ring. And so we get breakage here. And look. Where's my red? Here it is. because the sigma bonds to this carbon all remain the same, the chirality remains the same. We end up adding, using the nucleophiles bond, our new nucleophile right here. I've made one mistake. That should be a negative charge instead. Pretty straightforward. I've added a nucleophile to the most accessible position. I wonder what this looks like. Substitution reactions. Really, we're looking at an SN2 type reaction on an epoxide ring. Well, that's an alkoxide, and the second step of this is addition of water, and so, let's see. This can't be the hard part. HOH, Bronsted-Lowry acid, Bronsted-Lowry base, simple deprotonation, protonation step. Get out of the way. And so it certainly appears to me like the regiochemistry is still taking place over the carbon epoxide bond. It does not appear to me like that chemistry, the region of that molecule is changing, where that chemistry is imparting. I'm just going to draw this because I need some space over here to write what happens next. Hey, I remembered. And then the stereochemistry, it appears to me like the carbon that gets the new nucleophile bond inverts. We would see inversion of chirality here where this nucleophile has added, if applicable. Because the more accessible carbon is likely not chiral, no real change in chirality, even though we do still get backside attack, but you could see something like this. Certainly an example, so let's just write an example of this. Here's so if we were to react this epoxide with thiol, HS minus, and then follow it by water, we would expect these carbons here to remain the same. It's not chiral, but even then it doesn't change at all. And then we would expect to see inversion of that chiral center to form in favor of that new thiol bond. And so we see the carbon that gets the new nucleophile carbon bond, and so green has worked for this. The carbon that gets the new nucleophile bond, that's this one right here. That carbon inverts applicable, and it looks like complete inversion. I did not give myself enough space to write right there. But the idea being that this is definitely an SN2 type substitution, so we should see complete inversion of that chiral center, one product being formed. All right, so let's take a look then at the mechanism that governs acidic conditions. Acidic conditions, so we'll use the exact same starting reactant. And then in this example here, we will be adding our acidic species first, and then in the presence of a nucleophile. And so what I'm going to write for us here would be the example of what you would see as H plus over H2O is the way that your textbook writes it. So H over H2O. You might also see this as just H3O plus as well. But the idea being that we're adding some type of nucleophile under acidic conditions. And we want to ask ourselves what happens then. And let me even sub out the water. Let me just write this, because I want to keep this as general as possible. What I said would be our weak nucleophile. And so species that this would work with, what we will see this for, and I'm following around, like your weak nucleophile would be X minus, it would be water, it could be an alcohol. All of these are going to be your weak nucleophiles that are added in the presence. So you'll see this listed as HX, H3O plus, or H plus over ROH is the way that you would see these weak nucleophiles. And know that the H's here, the plus charges, are indicators that you are undergoing this reaction under acidic conditions instead. When we see reactions like this, the behavior is a little bit different, because now we have a Bronsted-Lowry acid that is already in solution, and at that point, we need to identify what that acid could react with. And our first unit we saw, and even up until the last unit, we've seen that proton reacting with the double bond. And now we're just acknowledging that it will react with an electron density about a heteroatom like oxygen. And so we have our Bronsted-Lowry base here as well. Electrons on this oxygen are susceptible for a proton adding. And what we observe at the end of that is we now have a protonated epoxide that has a positive charge on it. The next step of this reaction, so we had a Bronsted-Lowry acid-base reaction, so it should be reversible. The next step of this reaction then is just kind of the idea of what happens when you have a species that is protonated that needs to react. It doesn't want to adopt this plus charge. So what it's going to do is it wants to try and get this plus charge to a more stable carbon rather than on an oxygen. And so you have a ring opening. And that's interesting because, you know, you had nucleophilic attack step first and then ring opening. Here we have protonation first and then ring opening. And when we do this, previously we had broken this bond, carbon-oxygen one, because this carbon was more accessible. Now we're going to break this carbon-oxygen bond because it leaves behind the more stable carbocation. Primary carbocation, secondary carbocation. We're not going to be looking at this. We're going to be working with this. And so we just get the more stable carbocation breaking and forming, rather, from that carbon-oxygen bond breakage, which placed the carbocation in the more stable position. And now we have this nucleophile that is present, and I'm just going to write H here. nucleophile H. And when we've been kind of writing the word weak nucleophile associated with this, the weak nucleophile here, this is the part that makes it weak, is you have a proton here that makes it weak. Otherwise, like we'd have an O minus here, but we have an OH here instead. And this nucleophile still has a lone pair of electrons on it. It is not a full-fledged negative charge, is capable of adding to this position right here. But you have a planar carbocation, an sp2 hybridized carbon, and so you could have top addition where you have a new nucleophile bond that has been formed that preserved the chirality. It's on a straight line. It has preserved the chirality that you had previously seen with the with this three-membered ring. And then you just have bottom addition. This is E2 type substitution, straight out of the book. Where you have addition of that new nucleophile, and it's still got the proton, so it's plus charge, on the bottom side. And so you have retention and inversion of your chiral center as a result of that. Quite interesting. Then, at the very end, you likely afforded this with some type of acid, or there's extra weak nucleophile around. Typically, you're going to see water as your replacement that will just simply deprotonate this species to give us our deprotonated ether that would be formed, or new nucleophile. I'll just write this as base. New nucleophile that is formed, the new nucleophile carbon bond. So this would just be deprotonation to get us to our deprotonated forms. And so it sure appears to me that when we go back to our table over here, that the regiochemistry should be appearing. So I'm just going to write an asterisk, just like the Houston Astros. It should appear about the carbon-carbon epoxide bond, but I'm about to give you an instance where that might not always be true. I'll just write rearrangements are possible here. And then the stereochemistry, so the new, we're just going to continue this down here. The new nucleophile carbon retention and inversion which is enantiomers, are both formed. And so we would expect to see these products generated in an enantiomeric pair, which isn't necessarily optimal, but certainly the result of this pathway. One last thing that I want to show you then is just an example of this all in place. And then we will call it a day because my handwriting is deteriorating faster than I thought it would today. Let's take a look at reacting this epoxide under acidic conditions first. So we will be reacting this in the presence of H3O plus and then in the presence of methanol. And we will be taking a look at the products that could be generated from this reaction. I will be suggesting, I'm not going to work through the entire mechanism here, but at some point in time, we will protonate this species and end up with the species that just has this benzene ring attached to this carbon here instead of a CH3. But then that ring will break. And that's what I essentially want to show you here, is that upon that breakage, we will reach a point where our mechanism looks something like this. So it's the same scaffold as what's above here. I'm just going to put a plus charge here and draw an explicit proton right here. So we're looking, I just wanted to do the asterisk thing and say you have to be rearrangements. I challenge you to write one word and talk about something else at the same time and see how well you do. It's a skill that takes practice. I put an asterisk when we looked at the regiochemistry of the acid-catalyzed reactions. Why did I put an asterisk right here? I put the asterisk right here because rearrangements could occur. We have a secondary carbocation here that could potentially, if we satiate that plus charge with the electrons and the protons here, we would end up synthesizing a carbocation now that is benzylic resonance stabilized right here, which is significantly more stable, and then our methanol will add to this carbon right here, so that what appeared to be chemistry that should take place about the 1,2 carbon is now actually taking place about the 1, 2, and 3 carbon atoms because we proceed through a more stable carbocation intermediate. This species right here that's formed would lead to what we'd normally expect, but because that exists at a carbon that is adjacent to a carbon that could be benzylic stabilized and susceptible for nucleophilic attack, we would actually end up, and I'm just going to write after a few steps here, so following the same idea of nucleophilic attack, then we would have to undergo some deprotonation. The product that we would generate would actually feature the addition of our OCH3 right there at carbon 3 instead of at carbon 1 and 2. And I guess if I were to say this, I would use this new squiggle line that we've been introducing to simply denote that we would have, that should have been in blue, plus an enantiomer. You would have an enantiomeric pair. And so be aware that because this pathway proceeds through a carbocation intermediate, that we would absolutely expect it then to have the possibility to undergo some type of rearrangement. And so just be aware that that's a possibility. We have actually just blown through one entire chapter on ethers and epoxides. The unit study guide is listed for you to take a look at as you progress through this material. I'll say one thing before I sign off, which is simply we are getting rid of the Q&A sessions. They have no purpose but to get us together on Tuesdays and Thursdays. And typically people don't have questions. What I'd rather do, and I'm about to send out a note about this, is just send me your questions. Send me your content questions and I'm just going to work them out and start posting videos. And so these will be 3-5 minute videos of me working through problems. If you want to see me work through a problem, just email me and I'll make a video of it and submit it for everyone. That way we don't have to ruin our evenings. We can all go get wasted in the evening and still have a lot of fun and still get the content out there. And so that adjustment is going to be made for this week. Send your questions to me. I'll start posting videos on them. And if not, I will see you tomorrow morning. Have a fantastic Monday.